Hello everyone and welcome to a new recitation. Today we will be solving problems related to problem set number 6. So let's begin with the first problem. In problem number 1, it says for each of the following connections compute the factored load based on weld strength. Also check if the weld satisfy minimum and maximum weld size requirements. All plates and sections are S275 steel. Now here, as we can see, we are given in part A, the connection specifications. We have the thickness of the plate at the bottom is 8 millimeters with a width of 250 millimeters. The upper one in here with a thickness of 10 millimeters by 150 millimeters in width. We have the load P applied, and that's what we want to find, the factored load. We are also given the information about our welds. Here, as you can see, we have the fillet width A, the throat is 8, and the length of the weld is 150 millimeters. Similarly, here we have weld at all the side from here. So we are supposed to find the factored load. Now, first of all, if we want to consider the minimum and maximum weld characteristics, we can take a look at the table J2.4. So at this table, it specifies and says the minimum size of fillet welds is supposed to be based on the material thickness of the thinner part. So if we take a look at this here, the connection, this one is 10 millimeters, and the one at the bottom is 8 millimeters. Now, if we consider the weld in here, which is right over here, I need to find the minimum W. I need to find W minimum. So considering the location of the plates that I have the 10 millimeters connected to the 8 millimeters. So I'm going to take the 10 as the plate that is controlling. And if you take a look at the information, it says over 6 millimeters to 13 millimeters, the plate thickness, you would take the minimum size of fillet weld as 5 millimeters. Now, if we consider what we have in the problem, W is equal to 8 divided by 0.707. Now, the 8, as I told before, this was A given to us. So this is how you'd calculate W. Now, from here, it seems that it is equal to 11.31 millimeters. And from the table, W minimum is equal to 5 millimeters as well. So if we make a comparison, we are above the minimum condition that we have. So this is good. Now, if we check for the maximum size of fillet weld, as you can see here, we're comparing with the upper part. So in the upper part, T is equal to 10 millimeters. And we already calculated W, as I show you here, 11.31. This is what we have. So it says we have two conditions. If T is less than 6 millimeters, then W max is going to be equal to the thickness. And if it was more than 6 millimeters or equal to, then W max would be equal to T minus 2 millimeters. So based on this, I'm calculating W max, and it appears that the maximum limit is 8 millimeters. However, what we have is 11.31. Now, in this case, what we have is actually violating the code, and this should not be happening. So our case is supposed to be 8 millimeters maximum. However, if we proceed with what we have, 11.31, and consider the minimum length for welds. So first of all, it says the length of welds should be bigger than or equal to 4 by W. So if we calculate the length of weld in the problem, as we can see in here, this is 150 millimeters, and the other one is 150 millimeters in here. So basically, the weld we have, LW, is equal to 150 millimeters. Now, what about 4 by W? 4 multiplied by 11.31, 45.26. Therefore, our LW is bigger than 4W, and that In that case, we just satisfy this condition, which is good. Now, also, we can check if we need a reduction for effective length. Maybe the length we have is more than the limit. So I'm going to consider the length of the weld. Is it bigger than 100 W? So if we check, it appears that it is less than 100 W, and therefore there is no need for reduction. Now, on the other hand, after considering the limits that we have, after considering all the limits, now I can consider if there will be local shear fracture of base metal or not. So when you apply this load, you might have failure in the plates rather than the welds. How is that? If we consider, for example, you had this weld over here, what we expect when you apply this P load, there will be a fracture over here. And these two pieces will be separated at the throat of the weld. However, there is another way of failure that I would like to explain. Instead of having the failure in the throat of the weld, you might have the failure in the base metal. So the weld might come out taking a piece from the base metal, and this would completely go out from here as I'm showing. This part would completely go out, and if it goes out, of course, the two pieces are separate from each other. So we want to check whether this case will happen or not. So we have to consider if ultimate for the base metal is more than the capacity of the welds or not. Now, if ultimate for S275 is equal to 430 megapascal, and if EXX for the weld that is given to us is equal to 360 megapascal, multiplied by 0.707, it appears that the F ultimate is obviously bigger than the weld capacity. So therefore, there is no risk of having local shear fracture of base metal, and it does not control. So we are sure that the failure would happen in the weld itself. Now I can calculate the factored load based on the capacity of my weld, and therefore the capacity of the weld should be, of course, bigger than the factored load that is applied. Now from here, I can calculate the capacity of my weld connection by using this equation. And if we substitute everything we have, 0.75 to factor the capacity, 0.6 multiplied by 360. 360 is the capacity of the welds, FEXX. We have 8. 8 is the A value, or the throat, and multiplied by the length of all the welds that we have. Now, as you can see here, I have on this side 150 millimeters, the other side 150 millimeters, and this side, since it's not specified, it means that it's covering the whole thing, and therefore it's also 150 millimeters. And then I'm dividing by 1,000 to convert from newtons to kilonewtons. And it appears that the capacity for the welds is equal to 583.2 kilonewtons. And I can say, therefore, the factored load is going to be equal to 583.2 kilonewtons. Now, moving on to the other part of the problem, part B. In this problem, we are given this connection. So we have this plate connected in this way. It is connected to the flange of a wide flange member. Here we can see that the length of the weld is equal to 250 millimeters. And we have the weld at two sides. So we have this side and the other side as well. And we're applying the load P. Also, we're given the information for the welds. And we have everything we need now. We can continue. So first thing I'm going to check now, I will check if there is need for reduction of effective length. So if we consider the length of the welds, it's 250 millimeters. If we consider 100 W, now it was given to me in the problem that here the fillet width is equal to 10 millimeters, therefore this value is A. And to convert it to W, I will divide by 0.707. And obviously this would be less than 250. So therefore there is, sorry, the 250 is less than this value. Therefore there is no need for reduction of the effective length. Now continuing, we want to check if there is, if there will be local shear fracture of base metal. Again, I will take a look and check if the base metal is strong enough. And again, 430 is bigger than 0.707 by 360. That means that the failure will be in the weld itself for sure. After that, similar to what we have done previously, I will consider that the factored load, applied load, is less than the capacity of the welds. And from here, I will substitute in the equation that I have 0.75, according to LRFD, multiplied by 0.6 by 360. That's the factored capacity of the welds. Multiplied by 10, that's A. Multiplied by 2 by 250. Now notice that the length of the weld is 250, however, I'm multiplying by 2. Why is that? Because at both sides we have welds. And lastly, I'm dividing by 1,000 to convert from newtons to kilonewtons. And it appears that the capacity of my welds is equal to 810 kilonewtons. And therefore, I can say that the factored load that I can apply is going to be equal to 810 kilonewtons. Now proceeding with the second problem. In this problem, it says determine the LRFD design strength and the ASD allowable strength of 6 millimeter fillet welds. If EXX is given to us as 480 megapascal and plate is 275 steel. And we have the load applied over here. So as you can see, I have the weld at two sides. The length of the weld is 200 millimeters. And the fillet of the welds is 6 millimeters. So I would like to check for the limits. So I'm going to check if we need the reduction for the effective length. The length of the weld we have is 200 millimeters. And if we compare it to 100 W, again, 6 divided by 0.707. And it appears that 200 is less than this value, and therefore there is no need for reduction. Again, I'm going to check for the capacity of the local shear fracture of base metal. So 430 megapascal, that was for the base plate. Is it bigger than 0.707, 360? Yes, it is. Therefore, the local shear fracture of base metal does not control. Now, then I'm going to check the capacity of the welds compared to the factored load. And I'm sorry, I have to check something. Yeah, actually, I have a mistake in here. So if EXX is 480 megapascal, if we consider 480 megapascal in here and multiplied by 0.707, the value would be equal to 339 megapascal. And of course, the base metal is still bigger. Therefore, there is no issue. So this is not supposed to be 360, but 480. All right, now we want to consider that the weld capacity is bigger than the factored load. So I will calculate the capacity of welds that I have, 0.75 by 0.6 by 480. Yes, this is 480 is correct. And multiplied by A, the fillet weld, and multiplied by the length of the weld, 2 multiplied by 200, because of course I have the weld on both sides here and there, and divide by 1,000 for conversion of units. Lastly, it appears that the capacity of those welds is equal to 518.4 kilonewtons, and that would be the factored load that is applied. Now, notice that in the problem, it was given to us that the P value is at 30 degrees. Now, it doesn't really matter if it was 30 degrees, 10 degrees, 45, any kind of degree. It doesn't matter in any orientation. Both welds will be in shear. Therefore, the orientation of this force does not matter. and P at the end is going to be equal to 518.4 kilonewtons. Now, continuing with the third problem, it says using LRFD only, determine the fillet weld size required for the connection shown. Take FEXX equal to 480 megapascal and 275 steel for all plates. Now, as you can see in this problem, we have this connection. We have this plate connected to the other one behind it. Here I have my weld. The length of the weld is 250 millimeters, and I have the applied load P is equal to 140 kilonewtons at the specific orientation. So I have to determine the fillet weld size in this problem. So if we consider, first of all, the vectors of the force that is applied, I want to take the forces in the X and Y directions. So if you consider the one in the Y direction, you have the force equal to 125.22 kilonewtons in the downward direction, caused by the 140 kilonewtons at specific inclination, and 62.61 at the negative X direction. Of course, if this is your positive X and this one is positive Y. And you have all the forces set in here. After that, we should consider the information about the weld. We want to find the sectional characteristics of the weld. So for instance, I have drawn my weld in here. The weld that I have in here, I draw it down there. It has a length of 250 millimeters and a width of A. That's the weld fillet. So that's what we are looking for. A is unknown. Now, if we calculate the area for this weld, it would be equal to 250A. The moment of inertia about the x-axis, of course, the centroid is at the yellow point, so there is no parallel axis theorem. Basically, Ix would be equal to 1 divided by 12 multiplied by A, the base, multiplied by the height to the power of 3, and that would be the value for Ix. Now, if we calculate the moment of inertia about the y-axis, it would be 1 over 12 by 250 multiplied by A to the power of 3. Now, since A is to the power of 3, this would be a very small value, too small. You can actually neglect. To make your calculations easier and achievable, you do not have to consider this value at all for Iy. You can consider it as 0. After that, we can calculate the polar moment of inertia, which would be the summation of Ix plus Iy. As I said, you can ignore Iy. Therefore, Ip is equal to Ix. Now, after obtaining these sectional characteristics and having the forces in the X and Y directions, now I can consider the stresses. So first of all, I would like to consider the stress caused by the force in the X direction. I will take Px and divided by the area of the weld. So what is Px? Px is equal to 62.61 kilonewtons, converted to newtons, multiplied by 1,000, and divided by the area of the weld, 258. Now from here, that's the value that I would obtain. 250.44 divided by A, and it would be megapascal. Now, after that, of course, if you're considering this as millimeters, it would be megapascal. Now, if we consider the stress in the y direction caused by the force in the vertical direction, I have 125.22 thousand. This is the force. And divided by the area 250A, here you would obtain your stress in the y direction. So I have the stress in the x direction and the y direction. Now, what else should I consider? I have to consider the torsional effect caused by those forces on my weld. So, of course, each of these forces have a moment arm from this location to the location of, or the centroid of the weld. So the centroid of the weld is over here. And we have a moment arm, Ry, in here. And I have Rx for the other force. I have another moment arm in there. which is equal to 300 millimeters. So first of all, if we consider the torsion, I have 62.61 multiplied by 125. What's that 125? Again, that's Ry. Here is 125. And of course, it would cause a rotation in this direction counterclockwise. So therefore, it is positive. However, the other force would cause a negative rotation, clockwise rotation. So it is negative 125.22 multiplied by 300. 300 is the moment R. Now from here, it appears that the torsion is equal to this value as shown in here. Now after that, we can calculate the stresses in the x direction caused by the torsion. So I will take the torsion and multiply it by the Ry. What's that? It's the farthest point from the centroid. So the centroid is again over here, and the very far away point is at Ry. Now doing that and dividing by the polar moment of inertia, you would obtain the value caused by the torsion in the x direction, the stress in the x direction as shown in here. Similarly, doing that for the y direction, again, you multiply the torsion that you have by Rx. So Rx in this case, if we take a look at here, it would be better actually. If we take a look at here, here is your centroid. Now the rotation was like this, or the overall rotation would be clockwise, yes. So the arrows would be going like this. So at the beginning, we found that the value Ry in here is equal to 125. Now, when it comes to Rx, I have to consider this value. What's that value? It would be A divided by 2. So that value Rx is A divided by 2. Now, if you calculate this, it would also appear to be a very small value. I know you can also neglect, or if you would like, you can consider it. This is up to you. However, it would be very small and it won't affect your calculations much. So proceeding with what we have. Now, as you can see, I found everything here in stresses. And I have that A that I would like to remove. So how would you remove it? You would basically convert the stresses to forces. How would we do that? Of course, we want to multiply the stress by the area to get rid of the stress and have forces. So if we consider the force in the x direction, F dash x, which is this one, we will take this stress in here and multiply it by the area. So 250.44 divided by A multiplied by the area 250A. This would give us 62,000 newtons. If we consider the same thing for F dash y, the stress, the force caused by the force, can say, of course, you would get 225.22 newtons, which is like same as those values in here. Okay, now if we consider the last thing I would like to show you is converting this stress in here. So I have this stress in the x direction caused by the torsion. You will multiply it by the area in order to convert it to force in the x direction. So here I'm multiplying by the area, and therefore the force in the x direction caused by the torsion would be equal to 713,000 newtons. Now, we would like to calculate the required capacity for the welds, and it should be bigger than or equal to the magnitude of loads on the weld. So under the square root, we have the squared value of F dash x plus F double dash x, and similarly for the y direction as well. So if we substitute the values as the forces that we obtained recently, you would get that the required capacity for the welds is going to be equal to 786.4 kilonewtons. Now, the required capacity for the, or actually, sorry, yeah, this value, Yeah, this is going to be your magnitude of loads on the weld and also the required capacity or the factor capacity of the weld. So the required capacity of the weld would be equal to 0.75 multiplied by 0.6 by 480 FEXX multiplied by A, which is the unknown that we need, multiplied by 250, the length of the weld. Now from here, it would be equal to the value we have obtained, the magnitude of loads on weld, and you can basically solve for A. Now from here, solving for A, it appears that A is equal to 14.56 millimeters. And of course, it's hard to do it in reality, exact value. Therefore, we take something logical and easier to do. So we take A equal to 15 millimeters. You go above, but you do not go lower than 14.56. Remember this. Now, continuing with problem number 4, it says in this problem, determine the value of the loads, the factored loads according to LRFD and ASD that can be applied to the connection shown below if 7 millimeter fillet welds are used. We are given the information about the weld and the steel for the plates. Now, as you can see here, I have the fillet weld that goes in this shape, and I have the applied load P. So someone might confuse and say that, okay, I have these dimensions, 115 here, but does it include the 7 millimeters or not? Well, let me make this clear. What you have in here does not include the 7 millimeters. So actually your weld, something like this, plus 7 millimeters, goes down. I'm reaching here, plus 7 millimeters, and it keeps going. So those dimensions that are given to you on the drawing do not include the 7 millimeters. So this is the final shape of the weld that we have. Now, of course, it's important to, sorry, if we want to calculate what we need, the capacity or the P value that we need, we have to consider the sectional characteristics of the weld that we have. So in order to do that, first thing we have to do is finding the centroid of the weld. And in order to do that, of course, I have to consider the weld as section. So here I have chosen different colors for the weld pieces to make this easier to calculate and follow. You can basically calculate X bar. So let me give you an example for X bar. I have, for instance, let's see, we have 300 millimeters. I have this 300 millimeters in here. This one has the area is of course going to be multiplied by 7 millimeters, and you will consider the distance from we want the X bar, therefore we want to find the y-axis location. So I need to find the distance from here until this centroid of the section here. What would be that distance? Of course, it would be 150 plus 7 millimeters. Therefore, I'm substituting 157. And multiply by 2 because I have the other piece as well in here with the same information. Similarly, that happens to the other pieces as well. And if we calculate the rest, of course, here we have the summation of areas. So remember, guys, for finding the X bar, it would be the areas, summation of areas multiplied by X bar for each piece divided by the summation of all areas. Now, calculating the X bar, it appears that the location of centroid is at 103.24 millimeters. And if we consider the area of the welds that we have, the area would be 9,548 millimeters square. Now, someone might ask, how did you find the area of the welds? Basically, you find the length of all welds and multiply it by 7 millimeters, the fillet of the weld. So for finding the length of welds, of course, you will sum everything you have. So for example, the length of the piece in blue is 300 millimeters. The other piece in here in purple, it would be 150 plus 7 plus 7. So therefore it's 164, and it goes on. Then you multiply the total length of the welds by 7 to get the area of welds. So in here, as we can see in this drawing, after finding the location of the centroid, here is the location of the centroid that I have, at 103.24 from the datum that we set as a reference. And based on this information, I can find the distance between the force and the centroid of the welds. So this is 203.76, and it is located also far away by 150 millimeters, the force. Now we continue and calculate the other sectional characteristics, such as the moment of inertia about the x-axis. So I believe that this is very straightforward. You can follow easily. So I will be skipping this. You can calculate Ix from everything given to you in here. Similarly, you can calculate Iy, the moment of inertia about the y-axis. And after that, we can summarize our information, obtained information. So this is the area, moment of inertia about the x-axis and the y-axis. Lastly, the polar moment of inertia would be the summation between these two. So we have everything we need to solve our problem. Now I would like to consider the forces on the weld in terms of P. Since P is unknown, that's the thing I want to find. So in order to calculate or in order to find the forces on the weld, when you apply this force P, it will try to cause a rotation about the centroid of the welds. And because of that rotation, of course, you will have these arrows at the very far away points from the centroid on the weld that you have. So this arrow is supposed to be here, and it goes on like this. So for calculating the force on the y direction, we want to bring the forces at the centroid of the welds. So Py divided by the area, that is a stress. If you multiply it by the area, it becomes, of course, force. So P divided by the area multiplied by the area will give you P, 1P. Now, if we calculate the stress or the force caused by the torsion, now, of course, when you apply this force, it will cause torsional effect. So here we have the T, and here I have the Rx value, and here I have IP, polar moment of inertia. So as you can see, calculating the torsion, it would be P value multiplied by 150, it's moment arm, 150 plus 203.76 millimeters. So I calculate the torsion. Now also I'm multiplying by 203.75. Why? Because after obtaining the torsion, I have to consider the very far away point. So either I have this one or I have this point in here. Now, of course, this one is 103 and the other one is 203.76 millimeters. So I'm going to take this value and substitute it and divide by the polar moment of inertia. Lastly, I'm multiplying by the area to convert from stress to force. And it appears that the force in the y direction caused by the torsion is 1.9 P in newtons. Now, on the other hand, we have the force in the x direction caused by the torsion. So again, I'm considering the torsion in here, 203.76 plus 150 by P. Of course, these are the same for the torsion. Now calculating that and dividing by the polar moment of inertia. Lastly, I have the Ry value. What's the Ry value? It would be the distance from the centroid to the very far away point. Of course, this is the point that is very far away. And the Ry value is going to be equal to, you will consider this as 7 millimeters plus 150 plus half 150. So that will give you 232 millimeters. Lastly, I'm multiplying by the area. And from here, I have the force in the x direction caused by the torsion to be equal to 2.164 P, of course, in newtons. Now I have the forces. I can consider the magnitude of this force to calculate it from the capacity of the welds. So here I'm substituting all the forces affecting in the x direction and all the forces in the y direction. And it appears that the value would be equal to 3.62 P. Now proceeding and calculating the capacity of the welds that we have. So what do we have? We have 0.75 according to LRFD, 0.6 by 480 megapascal, that's for FEXX. And lastly, we have in our equation A multiplied by LW. So that is basically the area of the weld. And as we calculated previously, it is 9,548 millimeters. Now, on the other hand of the equation, I have the 3.62 P, which is the total or the magnitude of the applied load. So as you can see here, I can find the capacity of the welds, and I have the magnitude of the forces that are applied. So the only unknown in this equation is P value. Now calculating the P value from here, it appears that P is equal to 569.71. And that is actually a factored load according to last 569.71 kilonewtons. Now, if we compare the value that we have achieved with the solution provided to us in the solution manual, you see that the solution manual is 566 kilonewtons, and what we have is 569.71 kilonewtons. Now, the difference in here is very small, and that is caused by approximations on the way, either by me or by the person who solved in a different way to provide the solution in the solution manual. Therefore, this value is satisfied, or any kind of p-value you take is good. Thank you so much for listening.